All right, this is a big one. This is called the ratio test and the root test. They're two different tests. The ratio test is the big one. We're going to be using a ton going forward, and it pops up on a lot of FRQs. Slightly different problems, but the process will be very similar. The root test is a very small, quick one that we don't use a lot, but the ratio test is big. You have to pay attention to this because the algebra is going to mess you up. So notice I already wrote this. It says use this test when the series has a combination of polynomial, exponential, and factorial terms. What does that mean? I'll point that out when we get there. But I want to go through the steps of how you use the ratio test. So the first thing you always do, we will set up a ratio. And I will show you how to do this in a second. We will set up a ratio with a limit approaching infinity. And then we will do a second simplify using algebraic techniques. So simplify using algebra. There's a lot of ways to do that, which we'll get into. We'll have to either use exponent rules or some factorial rules. And then you'll get all the way down to an answer. And the possible results, there are 3 of them. 2 of them are good. 1 of them is inconclusive. So the possible results, you get the 2 good results. Either you get a number, a value, I'll say a value less than 1, and that means the original series converges. So if you get 1/2, 1/3, or 0, you can get 0 in this case. That means the original series converges. If you get a value greater than 1, that means the original series diverges. And if you happen to get a value equal to 1 at the end of all this, that is inconclusive. We can't use the ratio test. Probably because we had similar growth rates in the top and bottom, and it didn't work out the way it was supposed to. So sometimes ratio tests won't work. We're going to use it in cases where it's pretty obvious you're going to use it, or it'll say use the ratio test, and then you'll get a result. Either you'll get a number bigger than 1, or you'll get a number less than 1. So let's just do some. First example. Stick with me on this. The algebra can get pretty bad, but not impossible. So here's our series from n equals 1 to infinity. Check this out. I'm going to make it alternate. Okay. So this is a factorial. We haven't seen this yet a ton, but we're going to start to, especially using the ratio test. So we have a series. Oh, there's Newton. We have a series with an n factorial term, an e to the n term, and an alternating series term. That means this is a good time to use the ratio test. You also could try using the test for divergence or the alternating series test, but I want to show you how to do this with the ratio test. So yes, there are other ways you could do this one. So we're going to use the ratio test. You're going to use the ratio test. Here's what I said to do. Set up a ratio with the limit approaching infinity. So you take the limit as n approaches infinity. And you take the series here that you are given, and in this case, we actually get to ignore the alternating component for this, because if we kept it in, we'd get the same answer because it would kind of cancel out. We'd end up with a negative, and everything about it at the end, we'd have an absolute value, would go away. So I'm giving you a shortcut here. You don't have to include the alternating component when doing the ratio test. Just plug everything else in. And here's what you do. For the top of the fraction, because we're setting up a ratio, you take your series, and everywhere you see an n, you put an n plus 1. Factorial. So instead of n, I plugged in n plus 1 over. You see how I have e to the n? In place of e to the n, where I see the n, I'm going to plug in n plus 1. All over, and then you just use your original series. n factorial all over e to the n. So it's kind of like limit comparison, except we're not doing a new series we're comparing to. We're just taking the original series with n plus 1 plugged in everywhere there was an n. One more thing, we take the absolute value of this. So that's why we're never going to get negative values. We're always going to get positive values. We're going to do all the math, and we're going to get an answer that is either bigger than 1, less than 1, or equal to 1. So how do we simplify this? Well, immediately what you should do, this is going to get a little tedious, you should multiply by the reciprocal. So I'll keep this fraction on top as a fraction, but then I will multiply, flip whatever you guys, what's that, flip, swap, multiply, I don't know. Multiply by the reciprocal, that's all I'm going to say. And now you have some simplifying to do. So this is where you need to know your exponent rules. When you see a base to a number plus another number, we can split that up as e to the first exponent times e to the second one. It's your exponent rule in reverse. When you have the same base, you add the powers. So in reverse, we can split it back up and say we're multiplying the two with different bases. Or sorry, with the same base with the different powers. So that's kind of nice. That'll help us in a second. What about these factorials? Okay. Side note here. If you have a number plugged in for n, like let's say we plugged in 3 for n. 3 plus 1 is 4 factorial over, and we plugged in 3 for n, 3 factorial. Factorial just means a number times itself all the way down to 1. So this would be 4 times 3 times 2 times 1 all over 3 times 2 times 1. And look, the 3's canceled, the 2, everything canceled except for the first term. Similar logic here. When you see n plus 1 factorial, you can think of this as n plus 1 times, subtract 1 from it, so times n, times, subtract 1 from it, so n minus 1, times, and this just continues until, who knows, depends on how big n is. But similarly on the bottom, n factorial can be written as n times n minus 1 times n minus 2 times ... And something really nice happens with factorials. This n cancels with this n. This n minus 1 cancels with this n minus 1, and all these other terms are going to cancel with all these terms. So what do you have left in the numerator from this term? N plus 1. Similarly, look what happens with these other things. We have an e to the n in the numerator, and we have an e to the n in the denominator. How nice. So after we do all of this algebraic simplifying, and this will happen with exponentials, and it will happen with factorials, pay attention to what you have left in the top. We have an n plus 1 term in the top, all over. What do we have in the bottom? Well, we got rid of all these n terms here. We got rid of e to the n. All we have left in the bottom is e to the 1. And now we have to evaluate this limit. So what does this limit equal? Well, now you go by growth rate. So what does this limit equal? We have the top is growing linear, and the bottom's not. It's not e to the n, it's e to the first. Pay attention to that. It's just a coefficient or a constant. So in this case, the top's growing and the bottom's not. So this limit equals infinity, which is greater than 1. So therefore, the original series diverges. And you could have guessed that based on how the original series looked, because factorial is way faster growing than exponentials. So I already said that at the beginning of all this. So you could have known, oh, look, the factorial in the numerator is going to grow way faster than the exponential in the denominator. So this one definitely diverges, but the ratio test will help in other situations. So I wanted you to see it in this one. But you set the ratio, you multiply by the reciprocal, you reduce it down using this factorial trick and these exponential tricks, depending on what you have, and then you evaluate the limit. And evaluating the limit, you get those 3 results. Either you're bigger than 1, you're equal to 1, or you're less than 1. So remember, if you go to 0 here, you can say that it converges because you're doing the ratio test. All right, let's do another one. Next one. What about this one? N equals 1 to infinity n all over 2 to the n. All right. Remember, you can't just say, oh, the bottom grows faster than the top, so this converges. No, you cannot do a test for divergence to prove convergence. This is not geometric. It's not a p-series. It doesn't really fit. You could try to do a comparison, but not really, because you have to compare to a geometric where the top is 1. No, it's not going to work. The best time, or the best thing to do in this case, since we have a combination of a polynomial, even though it's linear, and the exponential, is use the ratio test. So ratio test. And how does the ratio test work? Anywhere, first we take our limit as n approaches infinity. Look at the original series. Everywhere you have an n, plug in an n plus 1. Anywhere you have an n, plug in an n plus 1. Oops. All over the original. Okay. Now, it's just like last time, we multiply by the reciprocal. So we keep the top fraction the same, and we'll simplify that in a minute if we need to. but we multiply by 2 to the n all over n. And now we do some simplifying. And the exponential should always reduce here, just like the factorials will always reduce. So we have a 2 to the n and 2 to the n plus 1. I'm going to write that as 2 to the n times 2. And what do you notice? The 2 to the n's cancel. And we are left with limit as n approaches infinity of, what do we have left up top that we didn't use? Well, it was the n plus 1. And on the bottom, we have a 2 times an n. All right, so what does this limit equal? Well, now we're at a point to evaluate the limit. Where's the growth rate bigger? Well, it's the same growth rate in the top and bottom. So since it's like the same power, we divide the coefficients. So this is 1/2. And 1/2 is less than 1. Therefore, this series converges. Imagine that. So even though your instinct may be to think, well, yeah, the bottom grows bigger than the top, that's not always the case. You need to use the ratio test. Otherwise, you are just guessing, and sometimes it doesn't work the way you think. So if there's a case where it converges, we got a limit less than 1. All right, one more. Here's a good overall kind of review of everything. So let's say it was this series. 3 to the k squared all over k plus 1 factorial. So this is a cool one. And we'll start at k equals 1 to infinity. All right. So this is a good one. Look at the growth rate in the top. The growth rate's not 3k or k squared. It's 3k times k squared. It's not a plus. So we don't really have a way to talk about combinations of growth rates. We can only compare singular growth rates. So this is a little different. So we are still going to use the ratio test, or in this case, we're going to use the ratio test, and see what happens when we do the math. So ratio test, because we have a combination of factorials, although in this case it's k plus 1 factorial, but all that is inside the same factorial. We have 3 to the k and we have k squared. So let's set up our limit as k approaches infinity. Yes, you have to set up the ratio. You get a point for this on the AP test. So k plus 1, k plus 1 squared all over O. What happens when you do k plus 1 plus 1? Well, that's just k plus 2 factorial. And then all over the original 3k, k squared, all over k plus 1 factorial. Bam. All right, same step. Multiply by the reciprocal. You're pretty much always going to be multiplying by the reciprocal, but I still need you to state the initial ratio. So 3 to the k plus 1, k plus 1 squared, all over k plus 2 factorial times multiply by the reciprocal. So the cool thing about multiplying by the reciprocal, and the reason why this works so well, is because similar terms end up on opposite sides of the fraction. That way we're allowed to do a lot of the simplifying that we end up doing. Okay, so let's deal with these factorials. K plus 2 factorial can be written as k plus 2 times, then subtract 1 from the next term. So k plus 2 minus 1 would be k plus 1 times ... Just gets down and down and down. Similarly, with this k plus 1 factorial, that's just k plus 1 times k times ... So a lot of stuff's going to cancel there. What about the exponentials? Well, we have 3 to the k plus 1, so we can write that as 3 to the k times 3. And now we are ready to simplify a bunch. So 3 to the k cancels with 3 to the k. All of this factorial cancels with this k plus 1 factorial. And what are we left with? We have a 3. We have a k plus 1 squared. We have a k squared. And we have a k plus 2. K plus 2, not factorial. So collect your terms, don't lose track, and write what you have left over. I see a 3 that I circled. I see a k plus 1 squared. And on the bottom, I see a k plus 2, and I see a k squared. So now we are ready to evaluate the limit. We have it all down to basically just polynomials. So what's the degree in this top? We have a degree of 2. Because if we were to multiply it all out, we'd have a 3k squared. But look at the bottom. we have a k squared times a k, we have a degree 3 in the bottom. So this limit equals 0, which is less than 1. Therefore, the original converges. So it turns out that factorial really is that fast growing, and it overpowers even a combination of things. So 3 to the k times k squared still isn't strong enough to overpower factorial. Factorial grows incredibly fast. But here's the ratio test to prove it. All right, so that's the ratio test with 3 examples. You're going to have to practice these. There's no way around it. You can't fake your way through this. When you're doing your homework, legitimately do this. I will be looking at your homework to see, because it's a process you have to follow. I don't give you a lot. You need to take the time with this. If you go through it quickly and it's wrong, I will be slightly annoyed, because this is all about setup and just following my process. Okay, one more. How about the root test? The root test doesn't come up a lot. It's very, very, very simplistic when you're going to use it. Basically, you're going to see a series that looks like this. And I will show you how this works on the flow chart, but it'll be n equals 1 to infinity. You'll have some function like 2n plus 4 all over 5n minus 1, except everything will be to the power of n. Kind of like a geometric. It's almost like a geometric, but instead of a ratio that doesn't change, it's like a ratio that has n in it. So the ratio is changing too. So this is all you do. When you see that you have an n outside of some kind of fraction, so there's an nth power. So you're going to use this when you see n as a power. All you have to do is take the nth root of the series and then take the limit. So you take the limit as n approaches infinity of, and you take the nth root of the inside with the nth power. And the reason is these just cancel. So the nth root and the n cancel. Essentially, you're just going to take the limit as n approaches infinity, ignoring the power outside and just looking at this series. Okay, this is where people make dumb mistakes. What is this limit? This limit is same power in the numerator and denominator, so it's 2/5. Now, if this was the test for divergence, that's a bad answer. That means the series diverges. So in tests for divergence, that means our series diverged. But we're not doing the test for divergence. Remember, we were doing the root test. So when you're doing the root test, what do you do with this value? You use the same conclusions as you did when you did the ratio test. So same conclusions from ratio test. The same conclusions that we used from the ratio test. So what is the conclusions? This was less than 1. Therefore, the original series converged. Which should make sense. If you thought about this geometrically, the ratio at its smallest point is 2/5. The ratio, well, I guess the ratio is always approaching a value of 2/5. So you can almost think of it as like it's a geometric with r equal to 2/5. So of course it converges. But that's why if you get a ratio bigger than 1, because the limit inside was bigger than 1, it would diverge. So the root test is essentially just used when you see n as a power. You take away the power, you do the limit of n approaches infinity, and you get your answer, and you use the ratio test conclusions. If it's less than 1, it converges. If it's greater than 1, it diverges. If it equals 1, it's inconclusive. We have to do a different test of some type. Okay, so that is the root test, which is less common than the ratio test. The ratio test is the big one. It takes practice for sure. So you need to invest time into this. This will be a major FRQ topic, believe it or not. We'll use it to do something called find the interval of convergence, which is later. All right, that's it.